Hello, everybody. It's great to be back in London again. Before I started in the Java core library team at Oracle a couple of years ago, I worked for a fintech company based here in London. And before that, I worked in California for 3 years. So I was thinking about for myself, which kind of English should I use, British or American? But I decided to stay with my Swedish accent. It's more like me. So there we are. Here's the agenda. Foreign function and memory API overview. We are looking at foreign memory, and we are also going to touch a little bit upon foreign function. Not so much, though, because we only have like 15 minutes today. We are going to do katas. This is a term derived from martial arts, and katas is a sequence of techniques that you can do. And then we have kind of useful patterns, and then we do something called fight, which when we use the patterns and do, in this case, a small microservice market info application, which I think is appropriate for London, where many people are working with fintech in the fintech area. So let's look at the foreign function and memory API. It's like kind of frowned upon to use native methods because it introduces a lot of security issues. But then again, there are a lot of libraries you want to use. We have off-CPU computing, we have machine learning, and we have graphics processing. And neither of those libraries are going to be rewritten in Java and should not be rewritten in Java. And so how can we use them without a lot of problem? And it used to be the case that we can use JNI, which is a Java native interface, which allows us to declare something called native methods. And the native methods are like an abstract method, you can say. They don't have a body. And then when we run the compiler, they will generate a header file, which we then need to implement in C. But this is kind of a brittle thing to do because it's like we have two languages. There is a transition back and forth between the different models. It's kind of hard to maintain. You have to be a programmer knowing both Java and C, or in fact, other languages too. And we all love Java, so we want to remain there, don't we? And it's also a bit inefficient because of these transitions. So if you have a Java client, you have a JNI in between, and then you have a native library. And this is how it works. So you have these native methods. You run the Java C compiler, and then a bunch of C headers are created. And then you write your own C implementation, or in fact, you can use assembler too, or any other language, as long as you adhere to the C interfaces. And then you create this shim DLL, which you have to load like this. So in this case, I'm writing a JNI method for getting the process ID. So I have this kind of user land code. I load the library, which is a shim library, getPid, and then I declare this native method here. And when I have a native method, I get this h.h file, which are the abstracts methods, and then I implement that single method up there, and it's just, delegate to the system called getPid. So just to reach that, it's a lot of mechanics, a lot of cogs that needs to be in place. So there should be a much better way, shouldn't it? Also, that was like when you call native methods, but it's also like how do you manipulate memory? Because often you need to provide some pointer or stuff to your native methods, like string length, for example. You need a pointer to a string. And JNI calling only supports primitive types and also direct buffers. And direct buffers are the abstraction layer for linear memory that we have in the existing JNI interface. And they can be passed to native methods with some drawbacks, and they can be accessed directly from C code. But there is no way to deterministically free or unmap such direct buffers. And you can only address so much address space because you only have an int as an index, so that's 2 gigabytes. In fact, it's slightly less. And it's like inflexible address and option, either sequential or offset-based access. And in fact, another big problem is that the direct buffers are mutable. Well, and we don't want to use mutable objects because we want to be able to share them across threads, for example. Yeah, and there is a lot of other frameworks that are trying to make this simpler. But we need something more Java-centric, something better, something more future-proof. And hence we have this JEP and the foreign function and memory API, which was a final feature in Java 22 after, I think, more than 10 years of work. So that's really good. So let's look at the foreign memory API. So instead of byte buffers, we have something called a MemorySegments, which provides a constructed model, a region of 64-bit address at memory, and that should do for some years. There are two variants. We have heap segments, which roughly corresponds to arrays, and then we have native segments, which is allocated outside the heap, and which you can, more easily send to a native function. It is important to remember that anything that are on heap can be moved by garbage collector. So the absolute address might change for a heap segment, whereas for a native segment, it will remain the same throughout its life cycle. Okay, the good thing with the native memory segment is that we will have size restrictions. That's called you cannot access a memory segment without out of bounds. So if there is a boundary, you have 16 bytes, you can't access something outside that. You will get an exception for that. There's also something called a lifetime. If you think about C, there are no lifetimes. You just allocate memory, and then you use it. And then you can deallocate it how on your own will. But the memory and memory API, foreign function memory API introduces something called a lifetime. And that makes it impossible to use that memory once it has been freed. So that's a temporal constraint. And there's also a thread confinement constraint, which is optional. And then you can say that I'm only allowed to use this memory segment by this thread. And that prevents, for example, data races or inconsistencies across threads. So here's a very simple example. Imagine that we have a point 2D, which is modeled with double X and a double Y. And this is C code, so I create a point with the coordinates 3 and 4. And this is how you can do that in the Java FFM API. Don't worry so much about the arena of auto. We will come there in a few slides. But what I do here is I allocate 16 bytes, because obviously this point is 16 bytes, because we know a double is 8 bytes. And then I kind of set the value for a double at position 0 to 3, and a double at position 8 for 4. It's going to improve, but I just want to show you how you can do it the mechanical way. And now, if I want to access something outside this area, I will get an index out of bounds exception, rather than just reading or writing to some random memory position. So this is a huge security improvement compared to working with raw pointers. So no out of bounds access, but there is no automatic deallocation here, because the arena of out is delegating to the garbage collector, and we have to use manual offset computation. So the auto, as I said, delegates to the GC, and that is, I think, one of the biggest success factors for Java is the garbage collector, which has the concept of reachability. So if something can, reach this in a different ways, it will remain there. But as soon as it's dereferenced and cannot be reached, it can be garbage collected. But we don't know when it's going to be garbage collected. And in fact, a byte buffer might be very small in terms of just the object itself, but it might hold a very big chunk of memory. And the GC is not aware of that. So we can have very small segments, very small objects sitting around, but they represent an allocation of huge memory segments. And they can maybe sit around for hours. And we cannot influence the removal of that. So the challenge is to provide a deterministic deallocation of memory. And what we want to do is also be able to model memory pointers that points to another memory segment. So we don't want memory to be free too early. That will give us use of the free problem. When we don't want memory to never be freed, that is a memory leak. And it's very apparent that C malloc free is too low level. How many of you have programmed in C before? That's a lot of people. And how many of you that are programming in C have access memory out of bounds. It should be the same number. Yeah, that's a very common problem. And we don't have this lifetime concept because you can just allocate memory, and if you have linked list, for example, you can just free a node and then you try to access that node afterwards, and boom, your program just crashes. Rust is a lot safer. There we have language construct for using memory, but it's a bit inflexible, for example, for cyclic data structures. So we have on the one hand, on the left-hand side, we have flexibility. On the right-hand side, we have full safety. So there's a balance to strike here. And here I have 2 examples of dropping the ball. In example A, I have a pointer to an object B that is being free. And if I follow that link, it's a use of the free error. And in another example, I have freed the C object, which points to D, but D is not free, so that's a memory leak. So, enter arenas. Arenas models life cycles of memory segments, and there are 4 built-in arenas. One called the global arena, which will always stay there. It will exist when the JVM starts up, and it will remain there for the entire duration of your process. And of course, it's good if you have, for example, a static final use of memory segments, and that will remain in your code forever. Then we just saw the automatic arena, which delegates to the garbage collector, and that is great for if you want to do something that's similar to the code you already have, like a byte buffer. That is also managed by the garbage collector, but that doesn't give you predictive garbage resource cleanup. Then there are 2 specialized arenas, one called confined, which says that only one thread is allowed to use all the memory segments that is carved out from this arena, and there's another one called shared. And the good thing with the confined is that it's cheaper to free it because you are sure that no other thread is using this. Whereas if you have a shared one, there is something called a thread local handshake when you are trying to close this arena, because we have to make sure that no other thread is using any of the segments that's been carved out from this arena. I mean, you can imagine that if we would have checked for every thread, is this freed, is this freed, is this freed for every access, it would be very slow. So we are kind of turning the tables, and when we are closing it, we are stopping threads that potentially uses this arena and memory segments, and see if we are in some critical sections, then we have to wait. And the good thing is that you can define your own arena. You can kind of delegate to one of these, and then you can have your own arenas. Maybe you want an arena that print out some debug information, or maybe you want to do something that does memory mapping, or do something else. Maybe you want to reuse your segments. And then you can write such an arena and just slot it in your application. So I think we struck the balance between flexibility and safety. So here is another example when we are using a confined arena. Note that we are using here try with resources. So when we exit the try with resource block, we are going to automatically invoke close on the off-heap arena here. So we allocate, we set the values, and then we know that all the resources allocated off this arena is going to be deterministically free when we reach this position here. And I can kind of try to leak this point. And if I'm trying to access this leak point after its life cycle has been closed, I will get something called a legal state exception already closed. So that's the protection against use of the free. Okay, so more happy faces, deterministic deallocation, no out-of-bound access, no use of the free. But still, it's kind of annoying that we have to do this manual stuff with the, keeping track of different indexes and so on. So then MemoryLayouts comes to the rescue because that allows us to, in a structured way, define different layouts. And we can use them programmatically and kind of use a declarative way to use our structs. So here is an example of that. You can see that the memory layout says struct layout. We have a double with the name X, and we have another double with the name Y, and that corresponds pretty much to the C structure up there. It should be noted that the layout is not tied to C. It can be any language or any data structure that you can model with layouts like this. There are also like arrays and unions that you can use. Eventually, a struct will come down to something called a value layout. And a value layout, for example, something models an int or a double, has a carrier type. So the corresponding for Java double is, of course, a double, and for the Java int is an int. So that's the carrier type. It also has an endianness, because different platforms have different endians. So you might, for most of the platforms, have little endian, but there are also someone who has big endian, and also for some protocols, like network order or so, is big endian. So you can set that in your layout, and your access will be adapted automatically using the endianness, so you don't have to worry about that. You can declaratively say that this is a little endian or this is a big endian. There are also alignment constraints, because some of the operations, like atomic operations, really must be on certain boundaries. And there is the concept of natural layout, which is a natural layout has an alignment which is the same as the size of the carrier type. So for example, an int is 4 byte, and usually it's aligned on 4 byte boundaries. Okay, so what can we do with these memory layouts? Well, we can query a layout and get something called a var handle. A var handle should be thought of as an accessor. And that accessor takes a memory segment and an offset. And then you can do things. For example, if you have a var handle for an int, you can access that as an int with said endianness and enforcing alignment constraints for atomic operations. And the good thing is that we already have var handles all over the JDK, so there's a lot of optimization in the JIT, so you won't lose any performance by using var handle. You might think that this is several steps involved there, but actually the JIT compiler is able to see through the var handle and optimize your code. So it will be almost as quick as just accessing memory by unsafe directly. There is also a combination API, so you can get the var handle and then you can manipulate it and get a new var handle, which has a kind of a higher order function. And there's a lot of libraries that support such combinations. So here is another example. We have defined our point2D, which corresponds to the C layout. We have var handles for X and Y. And then we can just use the var handle and say, I have my X handle here. I set the point at 0 and 3D, and then I have Y handle and set it 0 and 4D. And here you see that we're using offset 0 for both, because the Y handle has a kind of a built-in offset of 8, which double is 8 bytes. And you can also use the combinator to say that if I'm only using like 0 offsets all the time, I can just say that I want a var handle that always have this kind of 0 there, so I don't have to provide it, and then I can just not provide that coordinate, and then it's kind of free. So this is an improvement, but as you will see in the katas later on, we can do even better than this. But this is a good foundation to build on. And remember that if you want performance, you should not forget to declare your var handlers as final, because if you forget that, the JVM won't be able to do all the performance optimizations that you might want to see. So that's a very common mistake. Okay, look at the foreign function API. Now it spoke about memory. Now it's more like calling functions. So this is just to brief an example. Imagine that we have a function that takes the distance from the origin to the point we're having. That's Pythagoras' theorem. And then we can just use something called symbol lookup to find this distance, provided that you have loaded the library with this feature. And then you can use something called a native linker, where you provide a symbol and you provided a functional descriptor of the different types. So this type will return a double, as you will see in the declaration of C up there. And it will take something that's structured like a point2D. Remember that point2D was the X and Y coordinates. So that's a more composed structure. And then we just go about and create our off-heap arena. We allocate something that is of the point2D. We set the coordinates, and then we invoke this method here called the distance handle. and provide a point. And that will return 5. And this shows how easy it is to kind of work with native libraries. I will show another example of this in the katas later on. Performance is great. This shows the difference between J and I, FFM with a simple call, and there's a kind of special flag you can set for very short native calls, like if you want to get the clock time, for example, it's likely a very quick operation, so then it's even quicker. Up call is even better. So up calls is when you are calling from C up to Java. And there is a significant improvement compared to JNI in terms of performance. So this is an example of callback. And this is also an example of a tool that's called JExtract. So I showed how to do this manually, but there is an automatic way to create all the bindings from a library. In this case, I have invoked JExtract for the stdlib C library, and it will generate all the bindings for me for the native calls. So the method showed in bold here are method that's been generated by JExtract. So this allocate method, for example, gives me a C-compatible representation of this lambda, because a QSort takes a callback. This is actually a callback that compares two elements of whatever I want to compare using the QSort that's built into the system. And this is the actual invocation of QSort. So I invoke this on the array, which is unsorted up there. I have 10 elements of whatever it is. Each element is 4 bytes, and then there is my comparison function that's going to be called by the system on every comparison. And then I get the sorted list out. So that's great. And you can download JExtract from here or from here. And it's free, and you might wonder why it's not included in the JDK from the beginning. And we actually considered doing that, but the thing is that we don't see that there are a huge amount of developers that will ever use JExtract. It's maybe 5%. And the thing is also that JExtract is quite big because it's built on Clang and other tools that's included in this. So therefore, you have to download it, at least for now, separately, but it's very easy to do it. Okay, so here's the wrap. The FFM API provides safe and efficient access to native memory. We have deterministic deallocation. We have layouts to enable structured access. And it's very efficient. We are 100% Java. We don't need to write and maintain native code in other languages. And there is tooling too. Yeah, JExtract is a very good tool to, very quickly grasp an external library and just provide access point for it. So looking at the uptake of the FFM, there are a lot of prominent libraries that already today are using the FFM. So let's head over to the katas then. So I'm going to look at how to create a bean type wrapper so we can get rid of all this method handler, var handle stuff and use it like a normal Java bean. Then we're going to improve on that, and instead of using a bean, we are using a record instead. And I'm going to tell you why I think that is better. Then we're going to look at memory mapping a file. That is having memory that when I change it, reflects in a file that can be shared by other JVMs, thereby kind of paving the way for our microservice mini framework. And finally, we are going to perform some atomic operations. We need to do that because we are now living in a multi-threaded environment, and maybe we even have different JVMs that access this memory map file, and therefore we need this to make sure that everything works. And hopefully the demo weather is good today. And after that, we are going over to the fight, and that's a small microservice application. And we are going to create a memory map persistent queue where we can put messages via producer, and then we have a couple of consumers that can consume this persistent queue, and then we're going to run the demo, and hopefully that will work. Okay, so that was the last picture. Sorry for that. So let's head over to the code. Okay, so before I start, I just want to show this. I just added this native call. So in this example, I'm going to call the str length method here. So I set up a couple of things here. I have a native linker, which links to native stuff that we already have. And then there's something called a lookup, which enables me to look up symbols. So I take the native linker and I create a down call handle. Down call is when I call from Java to C. I know we all understand that Java is on top and all the other stuff is under, so hence the name. And what I want is, I want stir length. Stir length here. And even in Java 23, that's going to be an even better way. So I don't have to do this two-step thing. I can just say find or throw. And if it fails, I will get a very useful message there. I say that, well, I'm getting along as a return. And the thing I'm sending in is an address. And of course, that's the address of a C string. So here is my string. It's called ABC123. Great imagination there. I create my arena, allocate from this string. So this will take my string and convert it to a C string, which is null terminated. And then I will invoke this string length method, which I declare up here. And then I will print string S equals and the length. And hopefully this will print 6. So let's see about the demo weather today. What happens here? So I will run it. And it will say the string length of ABC123 is 6. Yay, success. We called a native method directly from Java without any JNI or any other languages involved here. So this shows that it's actually very easy to use native methods using the FFM API. Okay, so let's look at the bean wrapper. Before we go into that, I'm going to show you what I'm trying to model here. So imagine we have kind of a stream of information coming from an exchange, and we have a timestamp that says when did this transaction occur. We have a symbol which says that in this case it's Oracle, and I kind of coded this in a simple way. I coded time so we can easily read it. I mean, in a normal case we might want to use epic time or some other time representation, but I just wanted to code it like this. It's still able to sort it, but it's easier to read. The symbol I elected to code as an int. So I use all the ASCII characters and shift them around so I get an integer. And of course, the reason for that is I want this kind of interface or this data representation to be of constant size. I could do it with a variable length, but that will introduce a lot of complexity, and I only wanted to show the main principles here. We have the highest, the last, and the lowest kind of bid for the day. And right now this is integer, but you can imagine that we can model this as millicents or something else of arbitrary resolution. So this is kind of the getters, and for the first example I also have all the setters, which I call the market info updaters. So I can take a time and set it on my bean, same with the symbol, height, high, last, and low. I also have a bunch of utility functions here. So let's see. I'm using Java int little endian here because most machines are using little endians. And if I'm going to run this on a machine with big endian, my default Java int, which is on the right-hand side here, will be in big endian. So I would kind of want to lock this down in this program to always use little endian regardless of which machine I'm running on. And then I'll say that my layout looks like this. This is very, unsurprising. I have a long little endian with name time, symbolize high, last, and low. And this corresponds, of course, directly to the interface I'm having here. You see the similarities is kind of great. And then I have all my var handles. And remember again, I declare them final for performance reasons. I have the time. I extract kind of the element called time, symbol, high, last, and low. And this kind of static function here, just, we can check it out at the end. Where is it? Oh, it wasn't at the end. It was here. So it just extract a var handle with something called a path element. Of course, these struct layouts can be of arbitrary depth, but I only have one depth level here. So I just, get the field name with the group name here. I have a method that converts a string to an int, just shifting bytes around, and then the reverse is true here, symbol as a string, the other way around. I have a toString method that takes something that implements market info and produces a nice, clean toString. And I also have a method that converts a memory segment to a hex value because we want to be able to inspect that when we run code. So this is what I have. And here is the bean wrapper. So the idea here is to implement both the getter and setters, and I have a segment that I'm using as a backing data store. So the idea is to allocate a segment that is of precise that size that my data is, and then I just delegate to the var handles. So if I would like to query the time, I use the var handle for time and getting that from the segment, same for the symbol, same for high, and same for last and low. So you see the pattern here, and the same for the setters. So I use the var handle set instead, and I'm setting time, setting symbol, setting high, setting low, and so on. And this gives me this kind of nice, kind of bean-like approach. So from the outside, we don't see that this is backed by memory segments. So this is kind of a good way to model your data. And let's see, now we have a demo here, so we can see some of the pros and cons of this. So we start off as normal here, up here, creates an arena. We allocate something that is precise of this size and has the right alignments. Then we create this wrapper around the segment. And of course, if I print it the first time, everything will be 0, because when you allocate something afresh, everything will be 0 in there. I set the time, I set the symbol, high and low values, and when I print it, I expect it to print something like this. If I inspect the hex value here, I will see that I have the time here. Time was long, so that's 8 bytes. Here I have the int, which represents the symbol. You can see that it's Oracle in this case. I have high, last, and low, and you can see that high is 1 higher than the last one, and 6b is 1 higher than 6a. So this is likely correct. Then I'm trying to print this from another thread, and this will of course fail because we have allocated this from something that is an arena that's confined. And that's actually good, because if I would have been able to read this variable or this wrapper thing, this might actually be wrong, because there is no guarantee that when play memory semantics that my updates are actually seen by another thread. And then there's another problem here. Of course, I can't use this outside this block, because now my backing segment is freed, because when I go here, my arena will be closed, and hence the memory segment will be closed. So let's run this and see what happens. So it works in the beginning. We have market value with all zeros. We have then, when we set all the values, we have what we expect. And if we look at the hex code here, it's very similar to what I showed up here. When we have the time, we have the ticker value or a symbol and everything. But then we get an exception, wrong thread exception. And this is why when we are trying to read the value from another thread. And that shows that it actually works. And I couldn't even do this because we already got this exception up here. So I think there is a better way to do this. We can improve on this. So let's say that we want to model this with a record instead. So we have a market info record that has, time, symbol, high, last, and low. And that automatically gives us the getters. And we don't want to implement the setters because a record is immutable. And hence, it can be shared across threads. And also note that the record does not have a backing segment. It kind of materializes the segment and put all the value into the record itself. I'm overriding also the toString here, so we get the same kind of printout. And then I introduce something called a record mapper. And what is the record mapper? Well, a record mapper is something that can get something of a type of a record from a memory segment, and it can also set a record and write the values into a segment. So you can say that this is a deserializer and this is a serializer. And then I also have a method that actually returns the layout. We will see later why this is useful. And actually, this is something that we are considering adding to the FFM API later on. We have experimented a lot with this. So expect to see a JEP on this real soon. So let's go back to the record mapper kata, and we say that we have a record mapper, and every time we read or get something from a memory segment, we just create a new market info record here. And then we just as before, we just delegate to the var handles here. Time, symbol, high, last, and low. So this is, again, very mechanical. And then for the setter, we do the same thing. We invoke the setter for all the values we have here on the market info record here. And then we just return the layout. We already know the layout because we have a market info layout. So here is how we can use it. Let me just close this first. We create an arena. Again, we allocate enough memory, and then we create a record like this. We set the values, then we print it, and unsurprisingly, we will have these values that we had before. Oops, sorry for that. And then we invoke the market info record mapper and set it to the segment, and then we can inspect the segment, and again, it will show the same value as before. And then we can try to read it back again from the segment and print out another instance of the market mapper info here. And then we can also check if they equal, and they should equal because they model the same data. And now we have thread safety because a record, you can share it across thread, so we can you can do this, and also we can use it after we close the segment because now the record lives its own life and has its own life cycle. So let's run this. Sorry, where is it? It's here. Great. So here we have market info. We have the binary data. We create the other one, and they actually equal each other, and that's great. And here we print it from the other thread. Looks good. And also we use it after we have closed the arena. So that's great. Almost to the end. So now we are looking at memory mapping. So let me just close this one. Memory mapping is the process of providing a memory segment that is backed by a file. And before we do that, we have some kind of flags. So when I'm using something that was to write, I set the create, read, and write. And there's also another one called sparse there. The sparse one says that even though I have a large segment, the operating system is free to have a smaller file. So until I've used it, it will stay kind of small. But as I'm using it, it will be expanded. So in fact, I can create enormously big memory segments. I can create a 64 terabyte segment with sparse files just on this laptop. Of course, it will consume some resources, but file-wise, it's very efficient. So I need to create a file channel in order to do file mapping. So I create here a file channel on a file I call market info data here. And then I map my file, memory segment, via this file channel. I use read-write at the offset 0, and I only use the size that is precisely as big as I have to use in this case. And I use this arena that models the memory mapping, so when the arena closes, my memory mapping will be, unmapped. I print whatever I have here, so this should show something like address and the limit 24 because the size of my information object is 24 bytes. There is a predicate that can return whether or not my segment is mapped, so this should return true, obviously. And then I create this market info record that I had in the previous kata. I print it out, and then I use my record mapper to write it to the segment, and then I print it. And of course, now my data should also stay in this mapped file. So when I do this command here, we should see the same binary data as we see up here. So let's run this. Okay, so we run it. We have a mapped memory segment with a size of 24 as expected. The isMap returned true. We have our market data, we write the binary data, and the process finished. So let's see if the data is persisted in the file. So I can go here and I just copy this here. And then, where is it? There we go, that's the terminal. So I can just do that, and there we have the data. You can recognize Oracle here, for example. So that shows that we have used memory, but everything we did with the memory segment was reflected in this persisted file here. And of course, I can easily implement something that reads off this file as well. This is similar. Now I want to read, so now I only said read value here. I open my file channel for read only. I reserve the same size, and then I use the record mapper to read from that mapped section. And then, of course, when I print it, I will get the same value here. So this is the way to recreate the data I have persisted to the file. And let's run that for sake of completeness here. And wow, there we are. So we picked up the data that was persisted into the file. Last kata, I have 10 minutes left. So here, let's see, sorry. I introduced something called a header. Maybe I should make this a bit smaller. I hope you see it at the back. So what I have here is a header that will prevent threads for racing between each other. And I model it as a 64-bit layout. I use the first 4 bytes as flags, and I use the second kind of int portion as an index. So the idea is that the first one will have 1, 2, 3, and 4 for each and every thing I put on this queue. So I will have a header, and payload. And then I use these bits here. So bit number 7, I use as an acquired flag. And then I write data, and once everything is written, I set this flag called completed. So the kind of header will start off with 0, which is free. And then a thread comes along and acquires it. Then it will have the value of x80. And then when it's completed, I will have acquired and completed bit set, which is C0. So I have a class that kind of models this abstraction. I have free, acquired, and completed. I have my usual var handles for flag and index. And using these var handles, I can implement the acquire and complete methods. So the acquire method is using something called compare and set, and this is an atomic operation that will only succeed if I have this value here that is 0. And if I am alone and win this thread race, I will put in the value here, which is acquired. So this is how I model the kind of multi-threading mutual exclusion. And then I have something else called complete, which presumes I have acquired it, and then I kind of just add this bit here called completed. And this must always succeed. If it fails, there is something wrong, because then someone else is trying to write something into my code that I have already acquired. There are other ways to do it. There is something called get and bitpairs, or so you can have more granularity around this if you want. And there is another flag called is completed, which can be used to query whether or not this kind of header has been completed or not. And that's also using volatile access, which we will see later is important. And then I have a getter for index and a setter, and then a toString. So this kind of, I create a header here, print a segment, and then I create this abstraction around the header. Then I acquire this one, which sets the bits. And after acquire, I will see that we'll have something like x80 and index 0 here. I set my payload, which is not shown in this example, and I set the index, and then I invoke complete, which is kind of writes that now I'm ready with my data block. And not only does it flag this, and because we are using volatile semantic, we are establishing something called happens before. So the thing is that when threads are mutating memory and reading, and you are using data across threads, there is no guarantee that things happen in a certain order in your code. And that might be very counterintuitive. But when you are using this volatile read and writes, you are establishing something called happens before, and then you know everything that's been written when I read this, the same kind of volatile access on the same address is seen by the other thread. And after complete, I will have a mutex of C0 and my index will be 42. And if we look at this by hex, it looks like this. I have a mutex and I have my index here. So let's start and see what happens. And it works. So we have like initially 0, 0. After acquire, we have set this bit. And then after complete, we have this mutex, and we have the thing here. Okay, so that completes the first section of the live coding event. So now we're going into the next section, which is going to be tricky to do in 6 minutes. But anyway, we have something called a queue producer here, which is producing a value. It has an append method that appends a record on a persistent map file. And there's a close one, which actually will close the section, the backing segment. So what we do is that we open a memory map file. We provide this mapper that I showed before, the record mapper. So this is kind of a general solution. You can put in any record mapper here you want. We have a path. And then we create an arena, and we do all these file operations. I won't go through that. And then we do append. So the append will go to the position where we are. And as long as we are seeing a completed header, we will continue to spin, because we might have started this producer when there is already a lot of things in the queue. And then we also want to acquire the next slot. So if we fail to acquire, we just go to the next position, and eventually we'll succeed. And once we have that, we will, put in values. We will have a payload that we also write to the file. And here we're using something called as slice. So the slicing is that you have a memory segment, and then you can just say, I want this portion of a bigger memory segment, and then you know that you can't route outside the bounds of that. We set the value, increase the index, and that's it. So it's really not so complicated. So that's that. And there is something called a consumer, which is very similar. It's a bit simpler because we only have to read here. So we do the same thing. It returns an optional. So if there is something new on the queue, on the position we are, it will return optional with a value. But if there is nothing on the queue, we will return optional empty. And you can see that here. So if the header is completed, we return an empty. Otherwise, we read the payload, again using this mapper. And there's a close method, and it's very similar to the other one. So let's see how that works once we have this kind of thing. So we are setting up a queue path. Here I have a directory, which actually is my queue. And every day I'm using a new file. So I use this kind of concept of rolling file. So you can see here that I have data from yesterday, but this is today. And in this very simple example, I will have 3 different events. I will have 1 for Oracle and 2 for other IT companies here. I will start a new thread that will call my producer thread. And then we'll wait for a second, and I will start 2 other threads named consumer 1 and consumer 2 that will kind of tail all the information that are in the queue. And they will use the same method to do the tailing. And we can see the producer here. We create a list of these 3 static messages. And then we open the queue producer, which I've shown before, using this record mapper that we have that can take in a record and put it into a segment. I'm using this queue path, which we defined, and then I just iterate over the 3 events I have, and then I wait for 2 seconds. And that's it, and then it dies. And the consumer is very similar. I have something called a yielder here. We'll not go into that right now, because that's, I will then open the consumer, and I will do loop here forever. And if something is present, I will invoke this onRead event. But if nothing is present, I will invoke this yielder. The yielder is kind of a thing that will pause for a while. In this case, I will sleep 5 microseconds before I go back again and check the queue. Of course, I can do busy waiting, but that will consume a lot of energy. And maybe that's okay if I want low latency. So my onRead event here is like I just print it out, but you might imagine that I can have a map that I merge all the events and I keep the latest kind of info for each symbol here. And that will be a very easy thing to do. I just take the latest value and merge that into a map, concurrent map. Or I can, for example, maybe I'm just interested in Oracle tickers here, And then I can just put it on another queue and maybe have another microservice that picks that up and maybe drawing some web page or doing something else there. And this will, of course, when it starts, it will start and it will produce all this value, and then it will print and everything will be here. So let's run that. I only have 1 minute left, so here we go. So the consumer starts, the producer starts, and then you can see the information is coming in here. And as you can see up here, we have this new queue created here. And if we look at the queue, let's do that. Where is it? It's here. So here we are. And then we can look at the queue, and you can see that we have all these kind of 3 events. We have Oracle and the 2 other IT companies here. And that's it. We have shown how to call native methods, and we have implemented a very small, microservice network using the FFM API. And that concludes my presentation. And thank you for coming and listening.